Now to look at the other type of electrochemical cell, the electrolytic cell. Electrolytic cells require an external battery to drive or provide the charge for an otherwise non-spontaneous reaction. There are three general types of electrolytic cell processes. One is for electroplating, the other is for generating non-spontaneously formed substances such as chlorine or fluorine or anything that any element that's generally found combined with metals in nature or vice versa. And the third is for the purification of ores, mixtures of metals, alloys, impure metal mixtures. So if you look at the electroplating process on the upper left here, people generally want to plate silver or some precious metal on the outer surface of a piece of jewelry or a spoon or a key or something like that. So it's important that the source of silver, or the silver bar, is hooked up to the correct terminal of the battery, and that would be the positive terminal of the battery. And the spoon or key or piece of jewelry that's going to be plated on the outside with silver must be hooked up to the negative terminal of the external battery. So this way, as you can see, negative repels negative, so the electrons will go along the inert platinum wire and charge up the key or spoon, and the silver bar is in an aqueous solution of silver nitrate. Not only that, because the silver bar is hooked up to the positive terminal of the battery, positive attracts negative, so some of the silver atoms will lose electrons to that higher potential source, the positive terminal, and generate more aqueous silver cations in solution, which then, of course, positive is attracted to negative, will be attracted to the electron charged surface of the spoon or whatever needs to be plated. So it is very important that the correct terminals are, or the terminals of the external battery source are correctly hooked up depending on what you want plated. The only other thing to look out for is to what to call the spoon versus the silver bar, and nothing is ever going to change with this. The site of reduction is where the electrons are being gained by the silver cations. So we use the old mnemonic red cat. So this must be the cathode of the electrolytic cell. No matter what the electrochemical cell, wherever reduction is occurring, that is by definition the cathode. And here the silver bar is losing electrons. Losing electrons is oxidation, so this must be the anode, side of oxidation. So the anode, or the bar of metal that's hooked up to the positive terminal of the battery, will function as the anode, and the spoon or piece of jewelry, whatever, will function as the cathode in the electrolytic cell. In the setup in the upper right corner, you see the electrolysis of water. Now, water does not spontaneously turn into oxygen and hydrogen. In fact, the opposite reaction, the combustion of hydrogen, is spontaneous and quite exothermic and rapid and therefore explosive. But if one would want to generate oxygen and hydrogen from water, you would need an external power source, a source of charge, an external battery, a voltaic cell. So that would be the terminals of the battery would be hooked up by inert wires into the water, and given a high enough potential difference in the battery, hydrogen and oxygen could be generated via this coupling reaction. Now, as usual, oxidation occurs at the anode, so the oxidation of water generates oxygen via the loss of electrons. So we would label the blue terminal, or the blue lead, or where the oxygen is being generated, the anode, and the reduction of water, the gaining of electrons, really the gaining of electron density by hydrogen as it goes from water to hydrogen gas, is the cathode. So reduction at the cathode, and that generates the hydrogen. And in the overall net balanced equation, 2 moles of hydrogen are generated per mole of oxygen, so even if the test tubes were unlabeled, wherever twice the volume of gas is generated, that's got to be the hydrogen half cell, or not really half cell, but the hydrogen test tube. Now the minimum voltage battery required for this would have to be, given that the two half reactions both have negative, indicating non-spontaneous potentials. The oxidation potential for water is negative 1.23 volts, and under standard conditions, generating 1 atmosphere oxygen. The standard reduction potential for water is negative 0.83 volts. So adding those two together, you get negative 2.06 volts. So this external battery would have to have at least a 2.06 volt potential difference just to barely generate this reaction. So, of course, if someone used a 6 or 9 volt battery, these reactions would ensue overall spontaneously. Another thing you could test for is where the oxygen is formed due to the oxidation of water. There's an increase in hydronium or hydrogen cation concentration, so this solution would be more acidic, so you can add a drop of an acid-base indicator. Let's say litmus would turn red in that test tube, whereas where the water is being reduced, hydroxide is being generated. So this solution here is quite basic, and a drop of litmus would turn blue, and a drop of phenolphthalein would become dark pink or magenta. So oftentimes questions are generated: what was the anode? What was the cathode? Both of these gases are colorless. Nobody could tell which gas is the hydrogen or oxygen, but you really can because of that 2-to-1 mole ratio and volume ratio of hydrogen to oxygen being generated. And at the cathode, where the hydrogen is being produced, you get the basic solution, and where the oxygen is being produced, you get the acidic solution. So you can backtrack and figure out which was hooked up to the negative terminal of the battery and which was hooked up to the positive terminal of the battery. Lastly, if someone has an ore, a metal ore, let's say of copper, there would be copper in there, and other metals, let's say zinc, tin, etc., etc. And again, careful placement of this ore connected to the correct terminal of an external battery, which would have to be the positive terminal of the battery, as you'll see. And we want to extract the copper, or purify the copper, from that ore. So the other electrode would have to be pure copper, sample of pure copper, and that would have to be hooked up to the negative terminal of the external battery. So just by following the simple positive attracting negative rules, etc., etc., the copper atoms in the ore would lose electrons to the positive terminal of the battery, as would the zinc and the tin. So into solution, those aqueous ions would go: copper 2 plus, zinc 2 plus, and a mixture of tin 2 plus and perhaps some tin 4 plus. All of those aqueous ions. Now among those aqueous ions, the ions that tend to get most quote-unquote easily reduced are the copper. The least active metal has cations that are more easily reduced. So the copper that comes off of that bar of ore will then migrate to the negatively charged bar of copper. It's negatively charged because the bar of copper was hooked up to the negative terminal of the battery where the electrons travel. So this way, the copper will go off of the ore bar into solution and then get plated onto the pure copper bar. And because that's the side of reduction, that is the cathode, and the ore bar must be made the anode of this electrolytic process cell. The tin and zinc are either left in solution, or depending what copper salt was used, they end up just as some kind of sludge at the bottom of the container there.